Hi, I'm Manesh Mistry, and I'm a lead programmer at usTwo Games in London. And today I'd like to talk about a game we released in 2020 called Alba, a wildlife adventure. It was our first open world game, and there were quite a few development challenges, and I'd like to share some of those today. So we're probably best known for the Monument Valley games that were released in 2014 and 2017 as mobile titles and have just been released on PC. Our most recent title is called Desta, The Memories Between, but there I'll be talking about Alba, which represented quite a few new things for us. So to refresh your memory, I've got a 1-minute trailer that I can play. So Alba is a single-player, third-person open-world adventure in which you play this little girl who goes to visit her grandparents on a Mediterranean island for a summer holiday. And while she's there, you can run around, you can talk to the locals, you can take pictures of cute animals and the wildlife, and ultimately you find out that the nature on the island is in jeopardy. And the whole core theme of the game is about the relationship between human beings and nature and their coexistence. We worked on this game for 2.5 years with a team that started with just 2 people. With a very simple prototype that had a lot of the core features of the game and the main pillars present, scaling up to a game that had a team of almost 30 people. This represented the second time we'd ever released something on Apple Arcade. So for us, that meant not just releasing for mobile, but releasing on multiple platforms and ultimately launching on PC and consoles. Also, it's worth saying that the final year of development, 2020, was essentially all done under lockdown. So that presented some brand new challenges for us too. So things I'd like to talk about, I'd like to run through just the basic project structure and how we put things together. I'd like to talk about our world generation system using non-destructive and procedural tools. And then I'd like to go a little bit deeper on the performance challenges we faced when making this. So the project structure, this image here is just basically the scene view zoomed out with all of the scenes that we've got loaded in an additive multi-scene setup. They're kind of organized by location and content type. So for example, there are a bunch of scenes for the farm, one of which might contain all the quests for the farm and all the terrain tools and all of the animals. And because of this multi-scene setup, we required cross-scene references to be built into this. We used a combination of Unity's own GitHub repo for cross-scene references and our own custom solution. Ultimately, there are pros and cons to both, and you sort of need to figure out what works for you. And we kind of made both work for what we needed. We use a lot of Unity systems in the game, so that's a Unity terrain. We use the standard Unity nav mesh for all of our AI stuff. All of the camera work is done with Cinemachine, and we use the Unity input package, which was in preview when we first went with it, but was already in pretty great shape. So I think it was the right choice to go ahead with it. There's lots of third-party software we use, like Fungus for dialogue and some scripting. We use Wise for audio, Maya for all the 3D asset authoring, and Instalod for helping us generate LOD meshes. I think at the heart of our development style is that we really like to prioritize iteration and flexibility. So there's lots of gizmos and lots of custom tooling. And I think over the years of using Unity, we've gone progressively more and more comfortable and confident with just making editor windows and cool tools and gizmos. And that's kind of one of my favorite parts of working with Unity. So I want to dive into the world generation now. So specifically non-destructive world generation, meaning it's something you can iterate on in a modular and flexible way. So this is just a zoom out of the island where that's a Unity terrain with lots of foliage that has been entered in through the tree system and then combined with hand-placed meshes that we would like to sort of follow the contours of the terrain. And so initially we knew we wanted to use something to create a natural environment, and the terrain is a natural choice. So we had to look at, well, what does the Unity terrain system offer us? And so the built-in Unity terrain editing tools are like painting tools to allow you to sort of paint the terrain as if it was a picture in Photoshop. And it's really nice, and you can make some really beautiful things with it. But because it's like a painting process, all of your brushstrokes are destructive, and they sort of mix into each other, and then you can't pick up something you've painted in one area and easily move it to somewhere else and blend it around. So we knew we wanted something a little more flexible, especially because of the way we like to work. So we were quite inspired by the approach that Abzu takes, which is to have meshes and volumes that are placed around, and you render a height map of that, and it sort of acts as if the terrain is a flat sheet that lays down over these meshes. This is a really old GIF that I had to dig out because ultimately we evolved this further into what eventually became the solution that we used, which is rather than just having volumes and meshes, each of the volumes that you move around are procedural terrain features that contain some realistic features about them, but it still goes through that same process of being modularly moved around and rendered into a height map for the terrain. So this is what that looks like. So each of these gizmos are showing what happens sort of faked real time. We sped up these videos to get rid of the baking time, but ultimately what you're doing is moving these handles around, and each of the handles define a piece of terrain feature. So the kind of features that we support are ridges, valleys, and levelers. And so you use the combination of those to modify what the terrain is going to be. This generates an intermediate mesh, which can be previewed by a gizmo. It's not going to be exactly what the terrain looks like, but what happens is after that intermediate mesh is generated, we render the whole thing to a height map and then give that to the terrain system. And at that point, we don't even need all those input objects. So there's a really nice pipeline of having input objects that don't even make it into the build, but then a really nice terrain system that contains all that information. And we really like this approach of moving anchor objects around and essentially using the scene view for what it does best, for moving objects around and viewing things from multiple angles. So we use the same thing for roads. So being able to place waypoints for roads. We use it for foliage. So being able to move around a volume that represents where the foliage will appear, and then have a definition somewhere else that shows which foliage will be there. And this particular technique, and a bunch of these were also really inspired by Ghost Recon Wildlands, which is a very different game from what we make, but it's really nice to see what the big AAA studios do and kind of learn from the best. And then in the last picture on the bottom right, it's got the terrain splats. So how do we handle the terrain texturing? So essentially there are some rules that define what color the terrain should be based on the slope, and also you can override that. So for example, for man-made areas of this island, we can splat custom terrain splats. And so this is just a little bit of a closer look at one of the ridges that we have in the game. So a small island, all of the red gizmos on the left, the cubes define the anchor points that you can move around, and then there's sort of a semi-transparent mesh gizmo that you can see, and then each of the blue spheres represent the road waypoints. And the roads particularly, once the designer has placed those waypoints, the actual path of the road is calculated using a 3D A-style algorithm that takes into account the slope of the terrain. So the road can be modified so as not to create overly steep slopes. And then ultimately, with the roads, we just create a line renderer that will then render out to the height map, as well as the intermediate meshes that render out to the height map. And so that whole pipeline is a step-by-step process that takes all the input objects and spits out a terrain at the other end in a deterministic and reliable way. So we start with those terrain feature meshes that are rendered with a custom shader that essentially changes the color of the geometry based on its height, and we render that into a render texture from a camera that's above the scene. Once that's given to the terrain, it looks like this. So we've given the height map, we get a little bit of contouring, and we've got some flattening where the roads are placed. We've got the biome-based foliage scattering, so using the tree instance system to figure out which foliage should be scattered everywhere, and doing that based on the volumes that have been placed around. We generate the splat map, so that's quite a subtle difference, but again, like the ground is being textured, and that road is also just reusing the same line renderer that we use for generating the height map, we use it for generating the splat map. And then finally, all of the non-terrain objects that need to get snapped to the ground into the right places. Now, this represented a process that we could essentially run every time you've made some big changes to the terrain. Before entering play mode, you'd run this process. It doesn't take up any runtime processing. We don't even need the input objects. And so what that eventually represented was a really nice place where we could just do things before the game runs. And so that evolved into what we then call the world generation process, where one of the nodes is simply that terrain generation. And we could insert a bunch of other things that were really useful. So the first step is setting up the scene. So we have a particular scene that will contain all this generated stuff. And every time you run world generation, we can just trash the contents of that scene and generate them from scratch. And we also used a really nice feature in Git called git skip work tree that allows you to check a file in, so it can be referenced by the project in multiple places, but it will not recognize any local changes to it. So everyone can freely regenerate this file as much as they like. And then there are a bunch of other things that we realized we could probably do before the game starts, like generate colliders to block the character from walking places where we don't want them to. We could generate a texture that contains the positions of where all the foliage is, so we can play some audio when Alba runs through a bush. And then a bunch of other things that we know we need, like light maps and occlusion. And I think it's also worth saying that these steps are modular. So if somebody needs to iterate faster, they could choose to not bake light maps just to save iteration time. So yeah, the world generation system had a bunch of pros and cons, and we were quite happy with the kind of world it allowed us to build. So it's got kind of real-time editing, and I say real-time because the gizmos are previewable in real time, and you can do a simple bake in about a minute. But I know that with other kind of more physically realistic terrains, you're talking about server farms that are running this stuff overnight. And so compared to that, the kind of real time that we have here was quite nice to iterate. The world can always be regenerated from input. So as I said before, you can just delete the generated scene and you know you'll get everything reliably from scratch, including being able to do that in a continuous integration setup. So our Jenkins servers that we have set up can just build that in advance. Also, these terrain features are basically just game objects with mono behaviors on them, so they can live in any scene. They can be worked on in parallel, so people can be working on different parts of the terrain. There is a con with that, which is that if people are working on two pieces of terrain that are next to each other, they would have to collaborate to make sure the transition between them looks good, because you can affect neighboring areas. And I would also say that with these kind of powerful procedural tools, as the project progresses, people were getting progressively more and more scared to use them, because there's quite a disparity between how low resolution the input is, which is just a bunch of objects and parameters and things, and then the high resolution input of this really detailed terrain. So that's just something to be aware of if you end up creating quite powerful procedural tools. So that was world generation. I want to now talk about some of the performance challenges we faced. So to sum up, this is an open world game. We were probably around halfway through development when we realized that the game simply wasn't hitting frame rate on even the best devices. And even when you're on the best devices and the game's not running well, you know that there's a bit of a problem. And the reasons for that are pretty huge, and I'll try to dig into some of them now. So if you're making an open world game, there are probably some good assumptions you would make for the kind of technology you would need. You'd probably want content streaming, imposter-based rendering for LODs. You probably want to design the environment considering lines of sight and maybe creating like secret loading areas. These are all really good assumptions, but unfortunately, we actually didn't do any of those things. And the reasons are really complex and could probably make up a talk by themselves. But I would summarize that as saying, we didn't think we were making an open world game until it essentially was an open world game in front of us. And at that point, it was almost too late to go back and re-architect everything. And part of the reason why this is that I think the way we work here, I like to call discovery-based game development, where we genuinely don't know exactly what we're making while we're making it, but we're kind of driven by taste and our own instincts as developers and testing and core pillars that we've defined for the game. So the core pillars for this game were essentially could be summed up as run around in nature and take pictures of birds. And so we were guided by that. And I think that when the project got to a state that was pretty late, while we were still guided by that, there was technical feasibility growing in the background that was a real problem. And so we reached this point in the project where ultimately performance needed to take the highest priority. So I want to talk a little bit about our approach to performance. So ultimately, it's really important to make sure you're doing any performance work on your target devices and to identify what those are. So our target device was the iPad Mini 4, and we wanted it to run at 30 frames per second. And that was particularly an interesting device because it was supporting a high enough iOS version that we didn't want to exclude it. But it also has this weird combination of a high resolution screen and a GPU that's not necessarily powerful enough to manage it. So it's really like the worst of all worlds device. Performance must be very much driven by profiling tools. So this is a loop that we will regularly go through and is a really important loop to follow. So essentially you measure first, you get your baseline, and there's no changes made yet. You're just figuring out what the current situation is. You then optimize and then remeasure again to verify that the change you made actually has an effect that you can see, whether you made something better or potentially even worse. There are two different kinds of optimizations that you can do. There's targeted optimization, where you kind of pick a specific thing to optimize and you reduce that, versus baseline optimizations, which are the kind of changes you make that sort of affect everything across the project. And then another thing that's really important is automated profiling. I see this as a loop that sits outside the measure, optimize, remeasure, where 1 week later, 1 month later, 6 months later, you want to figure out if the changes you made when you optimize are still there. So it's really important to have a regular cadence of rechecking, and if possible, on target devices, that the frame rate is still consistent. I would say it's also important to catch spikes, not just averages. So if you just kind of average out what the frame rate is, you might lose the fact that standing in a specific place on the island and looking in a specific direction, the frame rate tanks. Those are almost the most important things to catch. So we've got to ensure that any statistical analysis we do on the frame rate data includes the fact that spikes are really important. And then lastly, you really want to focus on the worst case scenarios. It can be often tempting and easy to spot places in which there's a best case scenario where you can group together calculations or make things go faster just because of a specific set of conditions. But if the worst case scenario is also possible, those changes that you did before, at worst case, might even make your worst case even slower. So it's always important to focus on the worst case scenarios. So our first step was the measure step. And this is a little collection of images of all of the profiling tools that we used. So the first one here is the Unity profiler. It's the standard thing that comes with Unity. It lets you check C# scripts, it lets you check UI performance, and a bunch of different things that are really helpful. And I think in the past we may have stopped there, but there are far more tools that are really, really useful and all have their own reasons for existing. And I have to shout out Unity here for supporting us a lot in essentially kicking us, dragging us kicking and screaming through using these tools, which are quite difficult, but very, very important. So in the top row there, these are all the Unity inbuilt tools. So the profile analyzer, the frame debugger, and the memory profiler. I think of those four, the one that's most unique is the profile analyzer, because I think that one's only in a package. And what that does is it takes profiler data and does statistical analysis on top of it. So if you capture 200 frames in the profile analyzer will identify across all of those frames what's most expensive. And then it does something really cool on top of that, which is after you've made your changes and you want to check again, you can take another set of 200 frames and you can compare that to the first 200. And so you really get a nice comparison of where savings have been made. And then on the bottom row are very platform specific ones. So the Xcode frame debugger, the instruments time profiler, and instruments game performance were all really useful for us on iOS. So we could connect those to a device, and on device, we can do a frame capture to figure out exactly what's rendering, or the time profiler, allowing us to profile right down to the engine what's being executed, and the game performance profiler, which lets us look at thread usage. So with all of these tools at our disposal, the unfortunate answer was that everything was expensive everywhere. On the GPU, the Foliage was far too expensive, even though we were using imposters. The CPU render thread and the GPU were just overwhelmed with the sheer quantity of objects. On the CPU main thread, just too many animators that were expensive and lots of objects doing lots of work. And we were also starting to get out of memory crashes. So it's like there isn't even really one clear place to go. Everything was really bad. So we needed to do something. And the only real strategy we can do here is to prioritize and conquer. As I said before, it was almost too late to sort of go back to the drawing board. So it was time for us to start identifying which things we could work on and go at them one at a time. So the things I want to focus on and places where we actually tried to get some gains and mostly did succeed. There's foliage rendering. There's kind of a multifaceted LOD system that was ultimately accelerated by bursting jobs. I want to talk a bit about the hard to profile areas. There was the photography mechanic, which is an interesting gotcha. Some miscellaneous improvements, and then finally some custom analysis tools that we wrote to help us. So with foliage rendering, we tried using imposter-based LODs. If you haven't used them before, the image on the left kind of shows that when you zoom out past a certain point, the normal high poly tree essentially goes down to something really low poly, just a billboard that has a pre-rendered angle of that tree that will kind of allow you to render something really, really cheap once you go past a certain distance. And the bottom right picture is kind of us then finally using it and art directing it to create trees that worked. And they were really good. And I think they looked great. But unfortunately, as soon as we put them on device, they were not performing well at all. And worse than that, they were actually the worst performing thing on GPU, which was a surprise to us because supposedly this is the cheap way to do it. So this is a shot of the Xcode frame debugger, which when you capture a frame for that one frame, it will calculate how much time is being spent on every single shader, and you can sort it by the amount of time. And so the top item in that list was the shader used for each of those imposter billboards. And so the question really was, well, why is it so expensive? Like, it's not even like it was taking up so much screen space. It was really low poly, and we just didn't expect it to be so expensive. And so it started off a chain of investigation as to why that was. There was nothing obvious in the shader, but with some serious Googling and some brute forcing, we found out that the imposter shaders are using alpha cutout for transparency, which again doesn't really ring alarm bells. But if you're experienced with mobile development, you might already know what's going on here. And it's the fact that transparency of any kind breaks hidden surface removal on tile-based renderers for mobile. And what hidden surface removal does is that if there are lots of polygons overlapping and they're all opaque, the GPU only needs to evaluate the fragment shader for the frontmost polygon there. And it doesn't have to do any of the work for the ones behind, because we know they're all opaque. As soon as there's some transparency in that ordering, that optimization breaks, and they all need to be evaluated. And rightly so, because if you've got like a transparent edge of a billboard, you can see the other tree behind it. So you need to render all of those things. All of these optimizations were broken with alpha cutout for transparency. And that was a huge problem for us. And it also highlighted the problem of testing on the target devices, because we were not seeing this on desktop. It was only on these mobile devices. So what did we try and do? We essentially had to go to the art team and do a brand new art direction for the trees that involved no transparency and pure geometry. So all of the trees you see here are what eventually are in the final game, but each of the pairs shows something interesting. So the pair, for example, the tree on the top left is showing regular normals, and the tree just beside that has transferred normals. And that was really an interesting art direction choice to help us create almost the illusion of higher fidelity where we no longer have access to it, to make up for the fact that this is purely a geometry tree. And transferring normals is a really nice technique. And I think it created some softness in the trees and in the bushes that we wouldn't have gotten if we just used the regular normals. Also, now the fact that the trees were completely geometry based, it was really important that the LODs were made for them really well. And so InstaLOD was really helpful here for us to create trees that looked good from all distances. And here's a bit of a before and after comparison. I still really like the trees on the top, the original ones. I think they looked great. But actually the trees on the bottom are actually more cohesive with the rest of the art style. And this represents the kind of thing where the right kind of technical constraints actually encourages creativity in the right directions. And so while they might not be as detailed as the other ones, I think they're actually more congruent with the art style. And so next is the multifaceted LOD system. So it might be difficult to see in that image, but there are basically hundreds, if not thousands, of dots representing each of the AI animals and the NPCs and the interactive objects. And all of these objects were doing all kinds of work all at the same time, including having animators that were running. And this is basically far too expensive. So we needed a system to figure out how to have these things not do any work when you're not anywhere near them. So we created this multifaceted LOD system that could be used to control the visibility of animators, to enable and disable audio, or to enable and disable specific script behavior. And this is all driven by a self-contained distance and angle checking system that can basically be used by anywhere. It was just a nice place to essentially pass in an ID and some transform information and get back a distance in a really quick way and in a self-contained way. This was already giving us some gains to help turn these objects off, but ultimately with the help of Unity, we tried porting it to bursting jobs, and it brought the time down from several milliseconds to below 1 millisecond. And so that was a huge saving for us and really represented a big chunk of CPU time we could get back. I would say that one more thing we tried with that was to see if spatial partitioning would help us. It actually didn't. The kind of thing it did was essentially move work from one place to another place, because I guess that's what happens once you've taken most of your gains. And at this point, it was really important for us to figure out where else we should direct our attention to get some performance gains. So I want to talk a little bit about some of the hard to profile areas. And this is where the various Xcode profilers really help. So the time profiler is basically like a version of the deep profiler that works on device, but shows you calls all the way down to engine. It gets aggregated over time. So you essentially start capturing, you play for a little while and stop capturing, and it will aggregate all the calls that happen. But what's interesting is that it doesn't stop at the C# level. You can essentially see what happens when you call .transform. You can see how many API calls there are in the engine, and it sort of helps you to realize that, yes, you should probably avoid repeated Unity API calls because of how expensive they are. And there are a couple of examples in the screenshots that might be hard to see. But for example, one of our components, the most expensive thing it was doing was simply repeatedly calling .gameObject in a function. And we realized, well, that can be cached. There's no need for it to be done multiple times. And we immediately slashed the most expensive thing inside there. Sometimes it's not easy or obvious to make those gains, but it's good to know that it's possible and to know what's really happening. So another hard to profile area is CPU occupancy. So the game performance profiler helps with this. So that screenshot is a similar aggregate capture that shows in a single frame, I think, I can't remember if it's a single frame or not, but those orange blocks essentially represent where the CPU or a particular thread is waiting for something else, where it's preempted. This is the kind of thing that doesn't show up in any other profiler. And it's also not easy to find out why it's happening here. So this is the other reason why it's really important to look at all of these tools in conjunction with each other to figure out what's going on. I think one of the things we found here was that this was the only place where we could see the performance of the audio thread. We couldn't see it in any of the other profilers. So it really reiterates the benefit of using all of these tools. The photography mechanic. This is one of the main mechanics in the game, where Alba is able to pull out a camera and look around and scan and take pictures of animals. Right from the prototype, we were essentially doing this with two cameras. So there's one main camera that's rendering the world outside, and there's one smaller camera that's doing a little render texture inside. And I think one thing I would say is that if rendering is already an issue, rendering the world twice is obviously going to be way worse. So I recommend against rendering your game twice for sure. Unfortunately, there are things that will happen twice, like all of your culling costs get doubled, and a bunch of other things that just happen to happen for rendering that you'll pay double cost for those. Those are things that might be able to be optimized by the scripting and rendering pipeline, but I'm not entirely sure. And of course, it was too late for us to find out. So on the low-end devices, we really need to figure out how to do one render. And so the solution we went for is that the outside world gets rendered to a cube map over a series of frames, and then we can just switch that out for a very simple skybox. And so we can keep the full render inside the camera that Alba's holding, but on the outside, it's a fake blurred cube map. And there are times when you can see artifacts. So for example, in this shot here, if you're focusing on the character, you can see they're animating. But as soon as you look away, the cube map is not animating. And we figured, look, this is something we can get away with because it doesn't really get in the way of gameplay. So a bunch of miscellaneous improvements. So this is kind of a bit of a grab bag of things that we learned along the way. So we found out just from looking at the profiler that enabled but unused Cinemachine virtual cameras just take up CPU time. So disable those if you don't need them. Nice, easy win. There is a Boolean called physics.autosync transforms that basically will force the physics system to synchronize with transforms that might be changing. And it could happen multiple times across the frame. This is something you can simply turn off and call it when you need it. So it's not happening even if nothing changes. Ultimately, I think we didn't use this because it had some side effects, and figuring out those side effects wasn't necessarily worth the time we would get back. But it's there as a thing that could be helpful for anyone. When shaders are compiled for the first time, there's quite a few Unity APIs to help compile those shaders in advance. We use the experimental API, and there's some great documentation to figure out how to use that. That helped us to remove those hitches that you see when an object is rendered for the first time. There were quite a few asset import settings that are really helpful to reduce your memory baseline. ASTC texture compression, various types of mesh compression, animation keyframe reduction, lots of really useful ways to save memory. And also, if those things can be automated through asset preprocessors, that will just ensure that these things don't have to be remembered by someone. They just get taken care of by the pipeline. And on this slide, I've got a bunch of various windows that we'd written that are actually very unglamorous data crunching type windows that were really, really useful. So for example, one of them simply opens all scenes and counts their game objects and lists them by count. So like we can direct someone to a scene that has the most game objects, or something that scans all renderers and groups them by material and shader. So we can figure out how many things are being rendered by what, or a prefab family tree that lets you select an asset and walk up the hierarchy to tell you what it's a variant of and what variants it has. Or what we also did with the test runner is to add object validation tests that could get run before every build to figure out if objects are healthy. These are all really non-glamorous things that I actually found really useful. And I really recommend these things. They're quite easy to write and really pay off in the end. And then our automated profiling system was a loop I was talking about that goes outside the measure, optimize, remeasure. Something that allows us to call a profiling sequence by continuous integration or asking someone to run it on a specific device. And in our instance, what we did was all of those purple anchors on the map at the top where we teleport the character do a 360 rotation of the camera, also do a 360 rotation in first person, and then capture some statistical data about the frame rate. And this was really helpful to essentially just keep running either on a daily or a weekly basis so we can verify the fact that performance isn't simply getting worse. It was also really important for us in lockdown to do this because we weren't in a studio where we had access to all of our devices. So we really needed some system to make sure that we weren't regressing on performance. And so ultimately, after all of these changes and a whole bunch of things that I didn't get to mention, we were finally able to bring our low-end devices up to 30 FPS with a bunch of things like disabling real-time shadows, disabling post-processing, and tweaking LOD bias. Ultimately, our goal is to ensure that people can still enjoy the experience of Alba with sacrifices that weren't so bad that it gets in the way of enjoying the game. And of course, on the high-end devices, we had improved power usage, improved frame rate stability, and also we didn't need to make all these concessions. So we've still got a double render, and there's some nice post-processing that gives you depth of field. So we really wanted to make sure everybody could get the best based on their device. So ultimately, what kind of lessons do I think we learned? Ambition must be informed by reality. I think we were making something really creatively ambitious, and it's great, and that's how I want to keep making things. But without having reality as part of the equation, it's almost like you waste ambition in areas that were eventually going to be impossible anyway. And if you have enough reality informing what you're doing, then the kind of ambition you do is actually driven towards making the game the best it can be, given the constraints that you have. So ambition must be informed by reality. And I specifically want to say this is not about quelling ambition. This is about directing ambition. And then optimization must be driven by profiling. Those profiling tools were key in everything we needed to do, and they all served a specific purpose. So be driven by profiling and listen to what the profile is telling you, because it's ultimately telling you what's going wrong. And then finally, I just want to say that this project represented 2.5 years of development by lots of different talented people. So much hard work went into this game, and it was actually quite hard for me to pick exactly what to talk about. I would have loved to talk about our time of day system and the grass rendering and our dialogue systems and our animation pipelines. So if you've seen anything you like here and you think it's interesting, we are actually hiring. Also, if you think you saw anything that was ridiculous, please come and teach me your ways, and let's make some creatively ambitious games together. Thank you very much for listening.